All right, everybody, let's go ahead and get started. So we left off here last time, if that ever comes up. There we go. And that's the periodic table. Does anybody have any sort of idea of how much of the mass of the solar system is accounted for if we're on this first period, by the way?
70%.
Yeah, it's a bit over 70%. Because a large part of the mass of the solar system is the sun, and the sun is primarily composed of hydrogen, right? Anybody know if we get down to here, the second period, how much that one is?
90%.
Yeah, it's a little bit over 90%, and then all the rest of this stuff is fairly low amounts, iron being one of the most common ones, which is why you see a lot of stuff made out of steel or iron, right? And that's why we're composed of mostly stuff on the second period and above. Those are the primary components we're made out of. And then we look on the third period, and what we see is that those are the next major components. And then everything else is just trace, right? Because they're a lot more rare to find. Okay? All right, so all of the elements that are listed on the periodic table are made up of what is called atoms. An atom is going to be the smallest particle of an element that retains the characteristics of that element. If you were to try to divide things past the atom and look at even smaller particles, they just don't have the characteristics that we associate with chemistry usually, okay? That we associate with those elements. They're no longer copper, they're no longer gold, they're no longer aluminum, they're no longer carbon, okay? At that point, they're neutrons, electrons, and protons. Has everybody heard of neutrons, electrons, protons before? Middle school? Yeah? Some of you? Okay. Okay, fair enough. Now, the idea that atoms did not become scientific theory until about 1808. That was Dalton's atomic theory, is arguably the start of this. There's actually a little bit of argument whether what would constitute the beginning of this. Now, John Dalton, 1766 through 1844, developed an atomic theory that proposed the atoms are responsible for combinations of elements in compounds. And so this is Dalton's atomic theory. Number one, all matter is made up of tiny particles, and those particles are called atoms. Number two, all atoms of a given element are identical to one another and different from atoms of other elements. Okay? There's a lot correct in this. For the time period, amazing, right? Number three, atoms of two or more different elements combine to form compounds. A particular compound is always made up of the same kinds of atoms and the same number of each kind of atom. Not necessarily widely spread knowledge even today, which is a little disturbing. Number four, chemical reaction is going to involve the rearrangements, separations, or combinations of atoms. Atoms are never created nor destroyed in a chemical reaction. And that principle has been further expounded upon, right? Has anybody ever heard of mass is neither created nor destroyed? Okay. And that has to be true, right? So mass is neither created nor destroyed. Energy is neither created nor destroyed, is it? Okay? And so everything just gets changed. It never gets created nor destroyed. Very good. Okay. Now, where does subatomic particles come in? Anybody know what subatomic particles would be? Yeah, they'd be the next thing down from an atom, right? And so we have atoms, and those would be the elements. And then we go to subatomic particles, and those were the proton, neutrons, and electrons that you'd heard of before. Literally sub, smaller than atoms, right? By the way, does the name atom actually make sense in this context? Does anybody know what atomos means? Indivisible. Means you can't subdivide it. Okay? It's a Greek word. It was actually proposed by the Greek philosophers and argued extensively during that time. And So atomos actually means indivisible, and it does make a lot of sense, doesn't it? For example, it's indivisible in that you can't go lower and still have that element, right? But is it actually indivisible and you can't break it down anymore? No. That's what we're going to talk about right now, right? So the end of the 1800s, experiments with electricity, and this is really the big thing that exposed this, is electricity, and they were like, why in the heck does electricity happen? What's going on here? These obviously aren't elements. They're not big. They don't have any real weight. And so those experiments with electricity showed that the atoms are actually composed of tiny particles, and these particles, we refer to them as subatomic particles. These are going to be your protons, neutrons, electrons, of course. Showed also that some subatomic particles in an atom have charge. You're good. Yeah. I'll have to rearrange at some point. It's in a weird place, right? Now, so can anybody tell me where would this charge stuff come in? Why was it having to do with electricity? Yeah, electrons, electricity. Electricity has a negative charge. If you put it with something that has a positive charge, it's attracted to it, right? Okay, so electrical charges, these can be positive or negative. Two positive charges, if placed near each other, are going to repel. Two negative charges, if placed near each other, will repel again, right? And everybody's played with magnets, right? North and south on the magnets. Those are the positive and negative charges, in case you're wondering. The coloring actually matches, by the way. You probably noticed like your magnets had a red and blue sides usually. Yeah, they actually, that's sort of a standard. Yeah, that sometimes gets messed up. But if you place two oppositely charged particles near each other, what happens? They attract. Funny enough, I see product descriptions on Amazon all the time that say this thing's negatively charged, the rodent is negatively charged, so they attract. Like, still something apparently a bunch of people don't know, which is really messed up still, right? Okay, now, again, these are those unlike charges attracting. So in 1897, J.J. Thomson discovered that the cathode rays were streams of small negatively charged particles called electrons. Does anybody know what a cathode ray is? Anybody ever heard of a cathode tube? Okay. Have you ever seen those old TVs? And they had like the glass in front, right? And then they had the tube in the back? Yeah? And does anybody know that they were actually vacuum chambers in them? Yeah, those are actually cathode ray tubes. Okay? You've also seen them if you ever seen one of those old movies with the computers, and they have like the giant tube things on them. Glass tubes with a little, usually a light or something in it. Yeah. Those were also cathode ray tubes. The old light bulbs used to be based off that design. Interesting little factoid to those, if you took a TV, hooked it up to a much higher amperage voltage source, and didn't regulate it, you could actually put out x-rays. It would eventually burn itself out, depending on the quality, but some of those old cathode ray TVs can be used as x-ray sources. Yeah, pretty wild, right? And so J.J. Thomson actually proposed what's called the plum pudding model of the atom. And so in the plum pudding model, you're going to have the negative electrons, which are the plums, and then you'll have a positive pudding right there. And so the electrons were essentially suspended in a positive medium. And this model is incorrect overall, but has everybody seen plum pudding, by the way? Oh, thank you very much. No? Plum pudding's not a thing? You've all seen raisin pudding, right? No? How about the raisin and bread dish that they serve down here? Where they soak the bread in milk and it becomes like really... Really?
Like French toast?
No, no, it's not French toast. It's actually a type of pudding. It's called bread pudding. Yeah. You've seen it. Yeah, it's a thing down here, right? Yeah. Apparently not for a number of people. You're familiar with the idea that you could have suspended fruit pieces within a matrix of something else, right? Like a jello, a pudding, something. Okay. Okay. Well, that's what plum pudding looks like, okay? It has little fruit pieces suspended in something else, which is a pudding. Okay. So in 1911, Ernest Rutherford actually worked with J.J. Thomson and he developed a new structure for the atom. This was based on Rutherford's gold foil experiments. And so what they have here is a source of particles. They surrounded with lead and left a little hole right here so that you can have a nice coherent beam of particles getting shot out. Okay? And then they could direct this beam of particles at a thin gold foil. Everybody's familiar with gold foil? Yeah, literally gold foil. Super expensive now, but you get the idea. And so the beam hit. Now, if this model was correct, what should have you seen? If the plum pudding model is correct. It should have just hit and basically, bam, absorbed, right? Like you throwing something into a bowl of pudding, right? It doesn't go too far, does it? Yeah, it's not going to penetrate through, is it? Okay? It did not. The beam went through. In fact, the majority of the beam actually went through. Okay? Some of the beam actually got deflected and scattered off of the direct pathway. Some of it went just directly through, no difference at all. And a little bit of it actually got significantly scattered. Mm-hmm. It was electrons. Yeah. Yeah. Mm-hmm. What's up?
What's the name of the slides?
What do you mean, name of the slides?
I'm trying to find it.
Oh. So it's 36. It's the chapter 4. It's at the very bottom.
Okay.
Yeah. Because of my 24 fall. No problem. Now, so when you shot the particles through, some of them got deflected. This is what was actually happening here. Note at the time they didn't have naming for all these particles, okay? This was just the charged particle that had very little mass. All right? And we haven't actually introduced the exact parameters of the particles yet. I'm working you through the science so you can understand how scientific development happens. Okay? And so we had, at the time, nameless, lots of different names. Those damn particles get shot out when you have this thing. Okay? And they're hitting the gold foil, and some of them pass through, pretty good amount. Some of them get deflected. But what doesn't happen is you don't have them all stopping, do you? Okay? So what does that tell you about this gold foil here? And this is film, by the way. Like the old camera film. So that you could record where things got deflected to and actually tell what happened. Okay? Now, what does that tell you about this foil if most of the beam just passes right through it? Yeah, if you had like water and you're spraying it at something, right? And a bunch of it passes through, what would that tell you about it? Most of it's empty, right? Yeah. There's a lot of like holes to get through, right? So it's kind of like a screen door or something, right? You can spray through most of it. Now, if you sprayed a screen door, what would actually happen? Would it all go through straight? No, a lot of it would actually get deflected, right? Some of it just deflected a little bit. Some of it deflected right back at you and you get wet. Okay? Similar to this, isn't it? So it said there's a lot of empty space there and only small little pockets that are filled with some sort of mass that's going to deflect stuff, right? Okay. And what it's actually telling you is that we have nuclei here. Now, you're also getting told something else here. These right here are going to be positively charged. Oh, these were alpha particles, by the way. They didn't know that at the time. But they're positively charged particles, excuse me. Oh, wow. I'm crashing. That's great. Okay. All right. I got to figure out what's going on there. So we now have proof here that tells us things about this. That number one, most of it's empty, right? Number two, we have small volume, very small in volume, parts of these atoms that have a lot of mass and can deflect things, okay? So that tells us that we have some sort of charged region, and because these are going to be small atoms, you know, in the middle of nowhere, it's very likely that these are overall some sort of in the middle to make the thing round, right? Okay. The other thing it tells us is that we have space around these in which we have some sort of negative charge, because when we look at these elements, they're not positive or negative all the time, are they? They're overall neutral. And so we know we have to have these charges divided somehow so that we could lose a charge sometimes, but be neutral most of the time. Okay? All right. So the atom has to consist of a nucleus. This has to have protons in it. This has to have positive charge. The nucleus also has to have neutrons in it, and these are going to be neutral. Now, these wouldn't have actually come from that gold foil experiment. I'm going to skip along the experiments because there was actually quite a few that were required for this. Okay? And I just don't have time to go into all those. And you probably wouldn't be interested in all that anyways. But if you are, we can talk about it sometime. The electrons, these have to be drifting around, popping around somehow in a negatively charged. And they have to be popping around in an empty space. And they're around that nucleus. And so this is what overall we've got so far, right? We have electrons. They're around in an empty space. In the middle, we have a very small nucleus. If this nucleus was much larger, what would have we seen in this experiment, by the way? Yeah, we'd see more deflection, right? Less stuff could pass through. Okay? Okay, so let's go ahead and talk about the atomic mass unit. The mass of the atom is going to be due to protons and neutrons. These are going to be in the nucleus. Anybody know the sort of size difference that a nucleus would be to the electrons? So if you take the this area right here that these electrons are in, and you were to set that as being the size of a football field, so the football field is within this, okay? This would be a tennis ball. Yeah, that nucleus is a tennis ball. So it's way smaller, right? We're almost all empty space, okay? All right, so chemists are going to call the mass of these things an atomic mass unit, AMU. This will be the mass equal to 1/12 of the mass of the carbon atom. The mass of the carbon atom, which is 6 protons, 6 neutrons. When you actually do the math, what you'll end up with is that the proton actually ends up with a mass. We typically round this as 1 AMU, 1 atomic mass unit, but it's actually 1.007. And then a neutron, which we typically round to 1 AMU again and just say that, yeah, they have about the same mass. That would actually be 1.008 AMU. Now, If you look at the difference between these, what do we see? It's about 1/10,000th of an AMU, isn't it? Okay? And so the difference between these is actually about the mass of an electron. And that's actually because of that, in case you're curious. The mass of an electron, very, very small. It's a bit less than 1/10,000th of an AMU, which is that number right there. That's the average mass of an electron. Okay, anybody have any questions? So electrons weigh basically nothing, right?
How did they figure out the weight of a proton?
So what they did is they were able to figure out carbon had 6 protons and 6 neutrons. Once they did that, they just weighed a bunch of carbons. And so they figured out how many carbons would be in a sample through a reaction, actually. And what they did then is they went, okay, there's this number of carbons. We divide that number of grams by carbons. And then we divide that by 12. That gives us the MU. Okay. Now, in reality, what actually happened first, though, that was the conversion of it. They literally just said protons and neutrons are 1 AMU. And because they actually ended up being slightly different, we ended up with these numbers over here. Okay. And so that's that. Now, this is the subatomic particles right here. This is a summary of them. These are the symbols. Typically, you can talk about a proton by just putting a P, lowercase p. You can, if you want to be more specific and make sure people understand what you're talking about, put a P plus, okay? And that would say proton, right? Which is the positively charged thing. If you want to talk about a neutron, you could put N. If you want to be more specific and make sure they know you're not talking about some number or something, you can put N0, meaning neutral, neutron, right? Okay. And electron is E to the negative. You never put E because there's other things that would be E. And it would cause you a lot of difficulties. This right here is the charges. So the proton has a positive 1 charge. Okay. Neutron has neutral, no charge, right? And an electron has a negative 1 charge, or a 1 negative, okay? By the way, did you guys see that there's something weird about the order of the positives and negatives on these? Don't you usually put a +1, -1? Okay. The reason it's ordered like that is literally the definition of positive charge is proton, right? And so you can't have partial protons, meaning that you actually literally have a 1 plus 1 proton, 2 plus 2 proton, yeah, or 1 electron, 1 negative, right? Yeah. So it's actually a definitional thing. These again are the masses. This is locations. Remember, protons and neutrons are what are going to compose the nucleus, and then the electrons are going to be outside the nucleus. Note that every single time you see one of these atoms drawn out for you, the sizes are completely unrealistic. If we actually drew it so it was realistic sizes, you could not see any of these particles at all. Okay? You'd have to get out a microscope to see them. All right? So the atomic number and mass numbers. So all the atoms of an element have the same number of protons. This is going to give them the same atomic number. And so the atomic number is the number of protons. You got it. So carbon has what? 6 protons. Atomic number? 6. If I get another carbon, how many protons does it have? 6. A carbon from a human. Carbon from a plant. Carbon from a star. Yep, they're all 6. Very good. And so again, that is the atomic number. This is what the periodic table is organized by. This is that number on the top whenever you've seen a periodic table, and it literally numbers 1, 2, 3, 4, etc. off on the periodic table. The whole number, it's specific for each element. It can't be anything but a whole number. It's never fractional because you can't have parts of protons. You wouldn't have a proton then. The same number for all of the atoms in that element, equal to the number of protons in an atom, appears as the symbol of the element in the periodic table. Note that the symbol and number of protons are interrelated, right? Okay. If you have a different atomic number, do you have the same symbol? No. If you have a different symbol, do you have the same atomic number? No. And so automatically, if you know one, you would have to know the other. Mm-hmm.
So some periodic tables have like another number on there. Is that the mass?
It is. You got it. Yeah. Very good. So atoms of an element, typically we represent them on the periodic table as being electronically neutral. Okay? And so this means they have a net charge of 0. And because they have protons as the defining atomic number, without any electrons, what would be the charge of this thing?
Positive
11 plus, right? Yeah. Or positive 11, yep. And so automatically, if we're representing this without anything up here, that means we're representing it as a neutral, okay? And so that means how many electrons are coming with it? 11, yeah, it has to equal out, right? Yeah. Okay, so when we look at atoms that are neutral, which are the majority of atoms as represented without any charges written in, then we're going to have something that's going to be neutral. A neutral calcium atom, for example, will have an atomic number of 20. It has to have 20 protons, has to have 20 electrons, and it has 0 net charge. And we always do these by the net charge, meaning that difference in charge. Okay, can everybody get out your clickers? Okay. All right, folks, so how many protons, neutrons, and electrons does a carbon have? Okay, so how many protons does it have? 6, very good. I didn't give you any charge, did I? And so this needs to be neutral. And so how many electrons does it have? 6, very good. Is there any other options other than 1 that would work? No. And so which option is that? You got it. Okay. Yep. Thank you. Oh, yep. Cool. Okay, and it is D. I haven't really went over the neutrons yet, but you could figure that problem out without that part, right? Because we already eliminated all the others. Okay. So now we're going to be talking about the mass number. All right, and so the mass number is the other number that you were talking about that's on many periodic tables. It should be on all periodic tables, but sometimes they simplify them just to make it easier to read in abstract. Okay, that's that number that usually has a decimal place. It should always have a decimal place because those are measured numbers. Okay, this actually represents the number of particles in the nucleus. If you were to round that to the whole numbers, that would be the number of neutrons plus the number of protons, right? How many electrons would we have to get a whole number? 10,000. More than 10,000, actually. And so, that's not happening, is it? Yeah, our periodic table doesn't go up to the thousands, does it? So, yeah. when you looked at those numbers on your periodic table, did you notice they had fractions? Yeah, decimal point. Yeah. Those fractions are actually different numbers of neutrons. Okay? And we'll talk about those in a bit in isotopes, but that mass number is the number of protons plus the number of neutrons, right? Okay, so what if you took that mass number and subtracted off the atomic number right above it? What would you be left with? Neutrons. And so that's how you figure out the number of neutrons, right?
But if it's a decimal, how is it? You can't have.
You do the one it's closest to. Yeah, that's the normal isotope. Okay. So, again, we're going to represent the number of particles in the nucleus, always equal to protons plus the number of neutrons. Does not appear on the periodic table because it applies to single atoms only. And when we're looking at the periodic table, that's a grouping of carbons. Okay? That is the solar average, as it will. If you were to grab a sample of carbons on Earth, that would be the average mass you'd get. Okay? If you were to grab a sample of chlorines on Earth, that would be the average mass for each of those chlorines. Okay? Now, if I do an average number, does that necessarily mean any single person's ever going to land on it? No. Like, is there 2.1 average children? Is there a 0.1 child? No. That's not a thing, right? We calculate the number of neutrons, of course, through the method we just talked about. This being an example. So we have potassium here. We go ahead and round that mass number. It's 39 minus 19, which is the atomic number, and that would give us 20 neutrons. Okay? All right. So these are the compositions of some different elements. Anybody have any questions so far? Okay. You don't need to. You can just directly take this stuff off the periodic table. This is just the atomic number off the periodic table, right? This is the mass number off the periodic table. And then that's just, atomic number again. Difference between those two numbers up here. And that's the atomic number again because we're neutral. Yeah. Okay, so the number of protons, again, going to be the atomic number. The mass number is the number of protons plus the neutrons. The number of neutrons is the mass number minus the atomic number. And so remember that when we're talking about mass numbers, this is always going to be a rounded number. It's always going to be an integer, right? And that's because it's for a singular atom, okay? When we look at the periodic table, that is an average, meaning that it's not any single atom that's going to weigh that, okay? Does anybody know where the numbers of electrons would show up for mass? So if we do, you're right. I meant to say mass. So the mass of the electrons, where that would show up. So say we have a number that looks like this, 2.0001. That would be electrons down there. Okay? Like if you added up all the electrons on lead, they're going to show up in this number down here. Okay? So that would be the sort of differences you'd see in masses of electrons. All right, so again, if we look for this again, when we look at this, we see the atomic number down here, right? Everybody see it okay? Okay, and this up here is the mass number. If you ever get confused, can the mass number ever be smaller than the atomic number? Can the atomic number ever be larger than the mass number? No. So it's always very easy to figure them out, even if I forget everything and get confused, because one is two things combined, the other is one of those things, right? All right, now, this is isotopes, by the way, that we're going to get into. So, has anybody ever heard of isotopes before? Like carbon-13? Okay. Okay, and so isotopes is an element that has a different number of neutrons, right? So instead of 6 neutrons for carbon, you could have 7 neutrons, right? The 6 protons plus 7 neutrons gives you an overall mass of 13. And so when you talked about carbon-13 before, or when you heard of carbon-13, that's what that was, right? Okay. And you denote that with the mass number right here. So when we take a sample of atoms from a given element, some of them are going to have slightly different mass numbers. They may have an extra neutron or a couple of extra neutrons, okay? It can actually get pretty wide-ranging towards the bottom of the periodic table. But usually it's just 1 or 2. These are going to have the same number of protons, because if we have a different number of protons, that would be a different element, right? The other way you can think of this is your number of protons dictate the chemistry, okay? So the chemical properties of that element, those are dictated by the number of protons. The neutrons, on the other hand, don't really do any chemistry per se. They just slightly change the weight of it, right? And so they'll have different numbers of neutrons. So right here we actually have a bulk sample of magnesium. If we were to look closer at this, what we would see is that that magnesium actually has 3 different isotopes, and these right here are the different isotopes. And you can see that, again, their atomic numbers are all the same. The only difference being the mass numbers are slightly different, right? Okay. And so how do we represent this? Well, we're going to represent the particle of an isotope of a given element by putting the symbol of the element, which is right there, magnesium. The atomic number is going to go on the bottom. Do you actually need both of those? No, people drop the atomic number all the time, okay? That's why you've heard like carbon-13 over and over before, okay? Is because you don't actually need the atomic number, because carbon gives you the atomic number, right? The fact that it's carbon, that means it's 6. Up here is going to be the mass number, and you would actually need that if you're talking about different isotopes, wouldn't you? Because you can have different masses that are the same element. Okay. Did anybody realize something about Mendeleev's periodic table? He organized it by what? Atomic masses. Yeah, and so his periodic table would have had the isotopes as different elements, wouldn't it? And it would have been pretty confusing if he had the ability to separate those isotopes. But he didn't at the time, and that's why he tried it with masses first. So these are some different atomic symbols. They're indicating the number of protons, neutrons, and electrons for your isotopes. And again, that's the number of protons down there, the atomic number, right? You take the difference, and that is the neutrons, right? Mm-hmm.
So, no matter the isotope, you're always going to have the same amount of protons and electrons.
Yeah. Assuming it's neutral, you'll have the same number of electrons. Yeah, but you'll always have the same number of protons. Period. Has to be. Because if you change those, you have to change that symbol. Okay. That making sense so far? Fantastic. Okay, so let's try this out. There's 3 naturally occurring isotopes of carbon. We have carbon-12, carbon-13, and carbon-14. Let's write the atomic symbol for each isotope. State the number of protons, neutrons, and electrons in each of these isotopes. So go ahead and tell me, first off, what is the atomic symbol for carbon-12? C, and then we do what? 12 on top, very good. And the bottom is? 6. Perfect. Yeah, and then 13 looks like? Perfect. And the next one? 15 on top, perfect. Still 6, right? Now, technically speaking, you don't have to put the 6s. It's just not a properly written sentence, if you will. Okay? It's just more correct to do it. The number of protons for each of these? Yep, 6. And it is the same for all of them, isn't it? Yeah. Whoop. Okay. Number of neutrons. Top one is? 6. Very good. And the next one is? Perfect. And the next one is? 8. And that was always just the 14 minus 6, the 13 minus 6, the 12 minus 6, right? Okay. The number of electrons. Yeah, because we didn't say anything else, these have to be neutral, right? And so they would have to be 6 across the board so that the positive and negative charges balance, right? And there we go. So write the atomic symbols for atoms with the following subatomic particles. Ooh. Okay, so 8 protons. Yeah, you can get your periodic tables out if you like. Oxygen, very good. Yep, and what are we doing with the oxygen? Okay, so what would be the atomic number? Yeah, it's the number of protons, right? And so we go ahead and put 8. Very good. 16. 8 plus 8, right? And then it has 8 electrons, so that is neutral, isn't it? Okay. Okay, and so we go ahead and go to the next one. 17 protons, that would be what? Very good. Fantastic. And then 20 neutrons gives it a mass of what? 17 plus 20, which is 37. Exactly. Okay, and then we do 47 protons, and that is what? Yep, silver. Very good. Yeah, you're allowed to have full notes. So you can go ahead and throw a periodic table in there. Typically, I would have had a periodic table in the room, so I'll have to remember to print some of those out. Would somebody please email me and say, Dr. Clausen, please make copies of a periodic table and bring them? Okay. Because I'm used to having a classroom that has a periodic table, so I don't have to worry about it. Yeah. But I do not have that, do I? I guess I could project it. All right. Let's go ahead and do this one. So considering the following pairs of atoms in which the X represents the chemical symbol of the element, which of the pairs are isotopes of the same element? So to be isotopes, they have to have the same number of protons. And so we look at the bottom number, and that is? Yeah, right there, right? So these are the same isotopes. You got it. The other ones, not the same number of protons, right? Very fantastic. In which pairs do the both atoms have 8 neutrons? It's this last one, isn't it? Yeah. Because these are one lower than each other, and these are one lower than each other, that would have to have the same number of neutrons. Okay? Or you could just sit there and do the math, right? So 15 minus 7, 8. 16 minus 8, 8. Yeah. Okay, so you'll notice those atomic masses on the periodic table, they are not integer numbers, are they? Dang it, Dr. Clausen. Confusing junk. All right, so again, these numbers here, these are referred to as specifically atomic masses. They're going to be calculated based on the weighted average of all naturally occurring isotopes. So they're literally, if I was to take a sample from nature, I should average this mass if I was to average the weight of all those sodiums in this case. Okay? Does everybody know how weighted averages work? Okay. Okay. If you don't know, please talk to me. By the way, it's how your grade is calculated as well, son. In case you're wondering. It's the same way you'll figure out how, like, what do I need on the final to get this grade. Okay? Exact same math. All right, so Again, it's going to be the weighted average of all naturally occurring isotopes. So if we look at this number down here, we can actually figure out very easily what is the major isotope of something. Okay? So this number here rounds to what? 23. Very close to 23, right? And so what that tells us is that almost all the isotopes we find in nature are 23, right? And then there's a very, very small component that would be like 22. Okay? Very tiny. Carbon is very similar. 99% of the carbons, carbon 12. Okay? 1% of the carbons, carbon 13. Almost minuscule, ignorable amount, carbon 14. Okay? Oh, could somebody, thank you. All right, so it's not the same as the mass number. That's why there's a different terminology here. Atomic mass versus mass number. Mass number meaning for a single isotope, a single nucleus. Okay? The atomic mass, on the other hand, is the weighted average. And so most of the elements are going to have two or more isotopes that contribute to that atomic mass of that element. And we can actually see those right here. And then we can see those atomic masses. Okay? And so if we look at something like this, copper here, what does that number tell us? There's a lot of both isotopes, right? Yeah. In fact, they're almost equal, aren't they? Yeah. And that's what that number tells us. There's a pretty significant amount there. Chlorine, by the way, and a lot of the halogens have a pretty good amount in that area. Once you start getting lower on the periodic table, you get more of that, those different isotopes. And that's why you get numbers that have like a 0.5, 0.4 sort of stuff. Okay? Okay, right here we actually have magnesium. This has 3 naturally occurring isotopes. These would actually be the percentages for that weighted percentage. And so here we can see that the magnesium 24 actually corresponds to 78.7%, right, of the magnesium you'd find. And that's what that would look like in terms of a bar graph. Okay. All right, fantastic. So let's go ahead and look a bit at calculating that atomic mass. Here we have the atomic mass of 35.45 AMU for chlorine. This tells us that these are... What's up? Oh, I just was hearing somebody talking over here. Okay. Now, we have right here the chlorine 35 and chlorine 37. Now, the chlorine 37 is 24.24%. The chlorine 35 is going to be 75.76%. And so what we can see here is that together they give that 35.45, right? And again, there is a significantly higher percentage of the chlorine 35s, but the 37 is a pretty significant amount. Okay. All right, so how do we calculate that atomic mass? So we can use an experimental percent in abundance of each isotope of that element. We can multiply the percent abundance by your atomic mass of that isotope, and then we sum the total mass of each of the isotopes. So let's try that for lithium here. So lithium has 2 naturally occurring isotopes, lithium-6, lithium-7. If the atomic mass for lithium on the periodic table is 6.941, which isotope of lithium is more abundant? 7, yeah. It has to be significantly more abundant, right? Okay, so let's go ahead and try another one. Okay, so we have 3 naturally occurring isotopes of potassium. We have K39. You okay?
Yeah.
Okay.
Just took a little water.
Okay. Sorry. K40, K41, if the atomic mass of potassium on the periodic table is 39.1, which isotope of potassium is the most abundant? Okay. All right. Did we get everybody here? Yeah. Fantastic. Now, so that has to be the K39, right? Which is the one it's closest to. Okay, so let's talk a bit about electromagnetic spectrum. Now, this is kind of there's a lot of the universe and the world around you that this brings into relief and actually makes some sort of sense. Okay, we actually have a surprising amount of the electromagnetic spectrum knowledge that's sort of just dumped all around you all the time, and then you're like, why is that? Okay, so first off, we're going to look at this from the lowest energy to the highest energy. Lowest energy is up here, okay, and the highest energy is down here. All right. So if you're hit by, for example, radio waves, or you're hit by the electromagnetic radiation that's coming off of like power lines, this is fairly low energy. Okay. On the other hand, if you get up further up here, you're going to have much higher energy. And so, for example, over here is ultraviolet. What happens if I'm out under ultraviolet light for too long? Eventually I could get cancer, or I at least would get skin damage, right? Which is the sunburn. Okay. By the way, that's actually the lowest energy ultraviolet radiation that we're dealing with. If you were to deal with the higher energy ultraviolet radiation, that would actually just kill you within 10 minutes. Okay? You can actually use that to purify water and kill all the bacteria and viruses in it. Yeah. If we were to do that same sort of thing, where long-term exposure with X-rays or gamma rays, we would die pretty quickly, right? Yeah. Okay. Now, when we look at these, what these are is they are what's called waves, right? Or electromagnetic waves. And what they have is called wavelength, okay? And you can think of it a bit like it pops into existence, it kind of goes a certain distance, and it pops into existence again. And you can use the analogy of waves on a pond nicely to think of this. Has everybody seen waves on a pond or a lake or a river? Okay. Okay, good. Or the ocean? Okay. Okay. So these right here, these are the peaks. Everybody see that peak? Okay. And these are called troughs. All right. And the wavelength is the distance between the two peaks. Okay. This right here is the wavelength. The longer the wavelength, the less energy it is. The higher the wavelength, the less energy, right? If we have very short wavelengths, that's very high energy. Okay? Okay. So, radio. You're cruising around in a vehicle, you go and you can still hear the radio even if you're on the other side of a mountain, right? Maybe not as well, but you can still hear it to some degree. So those very long wavelengths let it pierce through things that are very thick, right? Like a mountain, okay? Or buildings. It actually pierces through buildings quite well, doesn't it? Okay. All right, and so if we look at this right here, we start getting up into here, and so visible light. Does that pierce through the wall well? Can we see outside right now? No, I can't see through outside. The radio waves are still getting in here, though, aren't they? Yeah. And that's a factor of that wavelength. That higher wavelength allows you to pierce thicker objects. Okay? Now, we look at this and we start going, what are all these things good for and what do they do to molecules around them? If we were to look at non-metals, the radio waves and microwaves basically just cause those to do very, very tiny vibrations, mostly just a little bit of rotation. Okay? And so they basically make molecules spin in place. Not a lot of energy. If we start looking up here, we can actually hit microwave radiation spots that correspond to things like water, right? If you pump a lot of that radiation into a very small space, we can do what's called microwaving food. Okay? And literally what we're doing is we're taking water molecules, we're causing them to spin. If something's spinning right next to something else that's spinning, what can happen? They hit each other, cause each other to start bouncing around, and that's called heat. Okay? And that's how you microwave food. You're actually causing the water molecules to start spinning and hit each other. Okay? If you don't have any water in the thing you're trying to microwave, what happens? It doesn't necessarily catch on fire, but what it does is it doesn't heat well. Anybody ever taken like a burrito and tried to microwave it and the center didn't get microwaved? That's typically because the beans and cheese and stuff in the burrito don't have high moisture content. So you don't have any water in the middle, and so it heats on just inside that outer skin. It gets real hot there.
Why does like you put metal in it? Yeah.
Good question. So, in fact, anybody want to try to guess the scientist that discovered this phenomenon and explained it? No. Unfortunately, that would be awesome if I was. That's Einstein. That's Einstein's big first discovery. Why that happens is that when we look at nonmetals, when we put them in the microwave, okay, nonmetals hold on to their electrons a lot better. And so their electrons don't get ejected until we get way up here-ish, okay? So we start ejecting electrons from nonmetals when we're up here. And when we're looking at a metal, metals don't hold on to their electrons as well. And so they'll start ejecting their electrons over here. Okay? And that's actually what you're doing. You're giving it so much energy in the form of electromagnetic radiation, it absorbs that, and it literally causes the electron to pop off that metal atom and then run across it. Moving electrons is electricity. Okay? And so we're literally shooting the electrons off it. That making some sense? Okay. Yeah, and that's why metals do that. I'm going to talk about nonmetals for all these, but know that metals just are shifted over this direction. It just takes less energy to do any of these things. Does that make sense? Yeah. By the way, this is like cell phone signals and stuff like that. Anybody ever heard of 2.4 gigahertz? Or 5 gigahertz, 5G? Okay. Those literally refer to what's called frequency. So you're literally referring to the frequency of the electromagnetic radiation. So when I said 2.4 gigahertz, that's the frequency. It's how often the peaks would pass through a given point. Mm-hmm. Oh no question. Okay. All right, so the next energy region is going to be the infrared. When the infrared is hitting things, it actually causes the molecules to vibrate. Okay? And so it'll cause molecules to start vibrating and shaking a bit. Okay? Again, it's mostly just in place though. It doesn't translate to a lot of motion. And that's actually, again, why you'd see like infrared coming off of things that are being heated up. Okay? Because they tend to vibrate when they hit each other a lot. Over here, we're going to see the visible light. Can you see this little tiny portion right there? Okay. Visible light is totally a kind of BS designation. It doesn't really have any special meaning other than we can see it as human beings. It is visible to us. That's it. Okay? It really probably shouldn't have its own region. And in fact, there are human beings that can see far beyond that visible region. It's called hyperchromism. and it's like a 1 in 1,000 thing for women. Yeah.
Do colorblind people still see in there, or is it like?
Yep, they still see in there. They just don't see all of it because they're lacking one of the receptors usually, or one of the receptors is malformed. Yeah. But yeah, basically they'd still see it. They just wouldn't see like this portion. Okay, and that would be red color blindness.
Why are men more often colorblind?
It has to do with our chromosomes. Women actually have hyperchromism, meaning that they can see a wider range of colors. And in about 1 in 10,000, 1 in 1,000 women, they can actually see up into the ultraviolet and see colors that the rest of humanity can't. Yeah, they totally have like a little superpower. And they can actually, overall, women can subdivide this region much better than men. And it's just because our receptors, we lack a duplication of that gene that would make sure that we'd actually develop that sensory ability.
Oh, is that why when you go to like 2 nail polishes, like
Yeah.
do, and they're like, that's the same color? Like, they're not at all.
Yeah. Most men can't subdivide. Yeah. Yep. And unfortunately, it is a genetic thing, so. Yeah. Anyways, that's visible light. The ultraviolet, meaning above violet, right? And so the highest energy visible light is violet. The lowest energy being red. Notice infrared below red. Ultraviolet here is the next region. You guys have all heard of UV before. By the way, does it pierce windows?
Yes.
Not really. Yeah.
My car window said west.
You shouldn't.
Sunburn.
Yeah, it's very unusual. You'd have to have very thin car windows. Yeah.
You know what?
Maybe, yeah. Double pane windows, though, and beyond, you definitely are not going to get any ultraviolet. Yeah. You can't tan through it.
Go be next to the window and test it.
Single pane, though, you might be able to get a little. You'd have to be pretty close, though. We get up here. This is X-rays. Everybody knows medical X-rays, right? Okay. This is typically the region where electrons just start popping off of nonmetals, by the way, like microwaving a fork. Okay? So if you were to just shoot somebody with a bunch of X-rays, they'd start zapping.
Magnifying glasses like amplify something, or just like concentrate it?
Concentrate it. Yeah. It basically just pulls in the radiation into one point. Yeah. And then gamma rays are very, very high energy. That's the sort of stuff that comes off on like a nuclear bomb, or you can actually get some of those from space, and they can get so high energy that they just penetrate through the whole planet. Okay? And yes, we oftentimes do get hit by gamma rays or high energy light from space, and it just like blows apart a part of our DNA. And that just happens like every day. Yeah. I know, right? It's very high energy coming in from the solar system, hitting people and objects on the planet, but because it's so rare and there's so little of it, it's not particularly meaningful.
So how do you know that you're being hit by it?
We actually have like huge detector arrays that we put into really deep mines that we can actually count these particles and see what they do. Basically, you have to put a bunch of heavy water into these big pools to try to slow them down and detect them. Yeah. Remember isotopes? It's the heavier isotope. So hydrogen is normally doesn't have a neutron. If you put neutrons on the hydrogens of water, that's heavy water. Yeah. So instead of having a mass of 16, or 2 plus 16, 18, it would have a mass of 20.
So what is the benefit of using heavy water over water?
Denser.
Yeah, does it make that big of a difference
Mhm.
to touch?
Oh, no. It wouldn't for you make any real difference. Like, it would be slightly more dense. You might be able to tell the difference if you were like side by side. but otherwise, no. Oh, okay. Yeah, though, interestingly enough, if you drink really purified water, you'll tell the difference. Yeah. It tastes very oily and gross. Yeah. It doesn't taste like your normal water. This water has actually been purified, then they added in salts to give it a taste. Yeah. Okay, anyways, that's the electromagnetic radiation. Anybody have any questions about that? I've only touched on it. This is one of those things I'm a I'm a real expert in. So, wow.
Hey, so is the exam still Monday?
It's Wednesday.
Oh, it's Wednesday now?
Yeah. Yeah, and what we'll do is Monday, if we are done with stuff, we'll move on to the next chapter, okay?
We have a review.
Do the review practice, ask me questions.
Is that going to be really similar to the exam, the review?
Yes.
Because that was a lot easier than that was easier than
Yeah.
before.
Well, yeah, the review practice, the homework is taking you through every single way you could do the problem, basically.
Incredibly difficult and the review is incredibly easy.
Well, partially you practiced in the homework.
No, but I feel like that review just didn't have half the stuff that the homework did. 90% of the stuff. It didn't have a lot of math. There was no math.
Oh, wow, okay. I'll check the review again, but it was same sort of questions I would normally put on the exam.
So does that mean that there would be less math? Hey, we don't have math.
Okay. What's up?
Will the exam be online or?
Paper.
How many questions would you say it is?
Okay, so we do have to move on at some point and get this stuff done, but I've already answered that actually a week ago, but
No, you said
so
time, not questions.
yes, I don't do the number of questions, I do the number of time. So I give you an hour's worth of questions. It depends on the type of questions I add in. So it could be somewhere between 30 and 40 questions. If I give you 30 questions, they took longer. Okay? Typical question would take about a minute and a half. Okay. No, you're good. You're good. I just need to. We had actually talked about this before, and I need to move on and actually cover the material that you'll have on the exam, right? And so, just need to do that. Okay. So, I do appreciate questions. We won't end up doing a separate review because I don't test over any specific part of the exam. Okay? Meaning that basically I'm going to test you on all the different subject matters as evenly as I can. Okay? I do appreciate if you send me questions though, and we can spend some extra time on those, and I can send out videos. So let's identify the form of electromagnetic radiation in each pair that has greater energy, yellow light or blue light, which would have a higher amount of energy in it. Blue, exactly. Ultraviolet light or infrared light? Ultraviolet, very good. X-rays or microwaves? Fantastic. So this right here is called the atomic spectrum. And if anybody's ever wondered how we go this star is composed of that, or that planet is composed of these things, and this is the percentages of those, that's actually because of the atomic spectrum. So when you have an atom and you've heated it up, the light that comes off of that is going to actually be specific frequencies, okay? And this would be referred to as a line spectrum, all right? Now, so for example, if we were to give a bunch of energy to barium, right? And then we were to take that and pass it through a prism so we can divide out the different frequencies of light, this is what we would actually record. And that would be the line spectrum for barium, okay? And notice, it doesn't fill the whole spectrum, does it? No, it just has very specific frequencies that will come out of this. And each element is more or less unique. Okay, they'll have a combination of frequencies that they will emit when they're being heated. Okay. So this actually corresponds to what's called the electron energy levels. And that's how high energy are those electrons. So again, that line spectrum, this being a line spectrum, right? Okay. This is actually going to correspond to exactly what energy level those electrons are in. All right. Okay, and so each electron is going to have a specific energy level, and again, that will correspond to the frequency of light it puts out. That frequency of light, these would be higher energy things up in blue, right? Lower energy things down in yellow, even lower in red. Okay. Okay, so these are going to be signed values. We're going to call these the principal quantum numbers. This is, by the way, why the N doesn't get used a lot. Principal quantum number is also N. These principal quantum numbers will be 1, 2, 3, 4. Okay? You can think of these like floors on a building, right? These actually are the periods on the periodic table, in case you're wondering. Where did the periods on the periodic table come? They came from these. Now, as we increase in energy, we're going to go up these principal quantum numbers. So 1 has the lowest amount of energy, 2 would have more energy, 3 would have more energy, right? So again, we can think of these as shelves on a bookcase. We can think of these as floors on a building. Okay? As we go up the principal quantum numbers, they go up in energy. And so if a book on the top shelf here fell on you, it would be more energy, it'd hurt more, right? If a book on the bottom shelf fell off, it would be less energy, wouldn't it? Okay? Okay, so this is actually what we refer to as quantized, because we can't put a book between the bookshelves and expect it to stay there, can we? No. And so it has quantized states it can exist in. Okay. Anybody ever heard of quantum mechanics? Okay. Guess where the quantum comes from? Quantized, yeah. Yeah. This is actually what quantum mechanics is based off of. Okay. Now the energy levels are going to increase as energy as the value of n increases. And so again, these will be higher energy levels that we can go to as we increase that. So when we have electrons that change from the lower to a higher energy level, what's going to happen is they are going to absorb the energy that comes in the form of electromagnetic radiation, i.e. light. Okay? This is going to cause the electron to go up into a higher energy level. And that's what we're seeing over here. Now, eventually, anything that goes up does what? Comes down. Yeah. And so eventually what's going to happen is this is going to come back down, and that will then emit a frequency of light. Okay? And those are those light lines on the line spectrum. Okay? They match up to these drop downs from higher to lower energy levels. And so if we have high energy photons being emitted, like instead of yellow, or we have a blue, right? What we're looking at is a larger distance between these energy levels. Okay? Okay. Is this making sense so far? Fantastic. You can think of it a lot like books on the bookshelf. If we have a bigger thunk, that meant a book higher up on the bookshelf came down, right? If we have a softer one, we have a lower book on the bookshelf coming down, don't we? Okay, so in each of the following energy level changes indicate if the energy is absorbed, emitted, or not changed. So an electron moves from the first energy level to the third energy level. If we're moving from the first to the third, what are we going to have to do here? We have to absorb energy, don't we? Or absorbed light. Okay? And this is why, for example, your shirts are the color they are, any of the objects around you are the colors they are. Is they have energy levels that are corresponding to absorbing the light that's coming in. Okay? And that's the light you no longer see when you look at it, right? And then the light that comes back out, that's the light that was emitted, isn't it? Okay, so an electron falls from the third energy level to the second energy level. What's going to happen there? We're going to emit light. And an electron moves within the third energy level. So it's still in the third energy level, it just moves around in there. Yeah, we're not going to have any change there, are we? Yeah, still on third energy level, no difference. Okay, so when we're looking at that periodic table, these are actually these energy levels right here. Those periods, those were the energy levels, that principal quantum number. Okay? Okay, so you'll see that I will simultaneously use 3 different words for this. It really depends on the context that it gets used. But they're the same overall concept, which is period on the periodic table, okay, energy level, and principal quantum number. They're the same thing. There's not a difference, okay? What we're looking at in the periodic table is literally lowest energy going to higher energy. And so it fills in as we go along in the periodic table. We're literally filling in these energy levels, okay? Kind of like filling a building in. We start at the first floor, filled in, then we go up to the next floor, filled in, and we keep doing so. Okay? So let's write the electron arrangements for the following elements. And while we do this, we're actually going to practice this electron configurations. Okay? That's literally how we arrange these electrons in these different energy levels. Okay, so before we start, we need to look at our periodic table. The periodic table is these energy arrangements. Okay? So when we look at this, we're on the first floor here, right? Okay, so we're going to fill in the first energy level. This is going to be 1. Okay? And then the next thing we need to do, when we fill in a building, we start filling in rooms, don't we? Okay, and those are places we can occupy with people. Okay? In the case of the periodic table, we're going to fill in what's called orbitals. Okay? And so right here, these are the first 2 orbitals. The first orbital, which we can fill electrons into. This is referred to as an s orbital. Okay? It stands for sphere. And so what it looks like is literally the sphere that you all come to know and love. Okay? Okay, we can fit in each orbital 2 electrons. And so how many different elements are on this first period, by the way? 2. And the reason there's 2 on there is because we can only fit 2 electrons in that space. So on that first energy level, we have an orbital which can then fill in up to 2 electrons. Okay? And so we fill in 1 electron, and that would be first level, the s orbital, we have filled in 1 electron. And so that's how we would write this. What this is it's the addresses of the electrons, just like you would do in an apartment building, right? Or in a school. At this point, we've only filled in 1 electron here. Yeah. If we go over here to helium, that would be filling in the second electron. And that would be 1s2. Because we've now filled in the second electron. We'll go ahead and pick up from here next time. You all have a good day. And if you have any questions on the exam, please send me an email or something. I can make up a little, hey, this is a reminder. These are the things for the exam. Okay. The reviews is a 1 and 2 review. Okay. This is broken into parts. I'll send an email to remind people, okay? You take care now.
Thank you.
Hey, have a great weekend.